Right, so now we're on to transfer.
This feels slightly weird on this side.
This feels very odd, I don't like it.
It's to transform.
I think it will. Get by matricey.
Translate.
Alright. Stretch. Not an eighth!
I wanted to grow.
Wayne, you're lucky. I'm shearing.
Okay. Anti-shear. Anti-shear.
Oh,
Anti-stretch.
that was good.
You can only do that once though, so next time.
I will be dead. Yeah, I'll be sad.
So,
How was the floor down though? Is that alright?
It wasn't very tasty.
No?
No.
I wouldn't have it on my chips.
No.
Alright.
That's why it's on the floor.
On it.
Yeah. So,
this is in a matrices chapter.
and it's about transformations
So we're going to transform stuff.
using matrices.
You're great. You ready?
So first let's use just a point rather than the shapes, just so you can see what's going on.
So we have some axes, and in our axes we have a dot.
I'm going to put it at the point 1, 2, we'll call it A.
Alright. So A is there.
1,
So
2.
to start with, I'm going to translate it. I'm going to move it by a matrix when you're ready.
Okay, so that's what the matrices are for. They show you what translation you're using. And you're doing 1, 0, 0, 1. That doesn't do anything.
No.
That keeps it exactly the same.
That is basically saying making those coordinates again.
But the way to explain it is, at this stage, it's got an x and a y coordinate, as you're familiar with, because it's a point on a coordinate.
And using this matrix, you are changing the x, this is the x part, the x coordinates by that, and the y coordinates by that, where that is the x part of the x coordinate, and that's the y part, and then that's the y part, x part of the y coordinate, and the y part of the y coordinate.
This will make sense when we get into an example. What Trev's done with this is important, you have to do that. After you've translated it, it will have an x dash and a y dash. It just means the new x and y.
And we call the new x and y what we create the image, what we started with, the object. That's quite an important thing.
That's an important thing as well.
Questions a lot.
You're on it with the important things today.
Thank you.
So this does nothing, because the 1, as Trev said, if we just draw up what Trev said, we've got an x and a y here, as Trev said. The 1 is x, and so it's times by 1 essentially. It stays exactly the same.
Yeah, and it's the same.
The y doesn't change.
Same as happened for y. But if we change our numbers,
yeah, you make up some numbers.
Okay.
So what it's going to do is this one's actually going to move the point.
So, try to just move. I'll change everything.
Okay. So 3, 4, 2, 2. Okay. Okay. So this is going to affect this dot so much that it's going to move to a new point. And the new point, wherever it may be, we'll call it V, it's going to be the new point, will have coordinates x dash and y dash, because it's not going to be the same.
Now we can form an equation that will sort of help us put in our coordinates and change from our object to our image.
And that's what the matrix is representing. As Trev's drawn it in a two-way table, you can see clearer what's going on, but that's what the matrix represents. So it'll be 3x plus 4y. That's going to be the formula or the equation to find your new x value after this translation. Similarly for the y, you've got 2x plus 2y will give you the equation to find out that. Now, I've noticed we have an x and y coordinate.
We do. I think maybe we could just put them in.
You're on it.
Alright, so let's do that.
Okay, so we've got 1 times 3 plus 2 times 4. 1 times 3 is 3, 2 times 4 is 8, so that's 11.
Yep, we have 11 here. That's our new x coordinate.
And for the y, you've got 1 times 2, which is 2, plus 2 times 2, which is 4, which is 6. So our new point B is going to be at the point 6, 11.
11, 6.
Apologies.
That's okay.
11, 6.
And that will be our new point.
So that's what the matrices represent.
Yeah. When we do it to a dot, it just translates it, moves it around our axes. We have a shape. That's quite a different effect.
It does. Because the shape is already connected, the length of the lines change, and that means something rather than just a translation.
It becomes interesting stretches. So to start with, you choose some simpler numbers and then get on to this sort of thing in a second.
Yeah. So, if we have a nice simple shape, shall we say a square? I like squares.
I like squares.
Then we could just have it, it could be just like this, with this point being 0, 0, the centre.
Okay.
This could be 1, 0. This point is 1, 1.
Okay,
really
the other one would
simple.
be 0, 1.
1.
Right.
And what I'm going to do is I'm going to give you an example this time.
Oh, okay, sure.
It's going to be stretched by matricey 2, 0, 0, 2. Okay?
Right. Okay. So now I've got these things. We do as always, put them into our point. And now I've got more than one point. So you have to put it into each one.
Yes.
So it is a bit lengthy process. So I'm going to call each one of these points a letter.
Yeah.
So can they be A, B, C when?
Yeah. Start here. A, B, C, and D.
Okay. A won't change at all because both the parts are 0. So when you times them, they'll just stay as 0.
Yeah.
So I'm going to start at B.
We just need an equation, and then we can apply it to all 3 points.
Yeah.
So the equation will stay the same for B, C, and D, but because they're different points, the answer will change.
So our equations will always be
2x
2x
plus 0y, so you don't really need to write it. Y dash is 0x, you don't really need to write it, plus 2y.
Then we just put them into our equations for each one.
So B is at the point 0, 1. So for its x value, it's going to be 0 plus 0. So it's just going to be 0.
Okay.
That's what its x value is going to be, which it is at the minute anyway.
So that's okay.
Its y value is going to be substituting 1 into here and 0 into here, so it's just going to be 1.
Okay.
No, it's not. It's going to
It's
be 2,
2, so
sorry.
we're going to have 2 times y.
Yeah, read it wrong.
So that's our new B one. Then if we change our C one,
Yeah, we're doing the same thing. We've got 1 and 1 for our x and y, so it's going to be
2, and that one also be 2.
2.
And our last one, which is D,
Is 1 0, substituting into this, gives your x value of 2, and the other one is 0.
so then we can plot our new values.
This is 0, 2, and 2 is going to be out here somewhere. And then 2 0 is going to be in line with that, but down here.
So this is the simplest stretch you can do, and it's sort of like stretching it scale factor 2 in like both directions.
yeah, because only the x and the y has been changed and nothing else has been altered, it does just stretch it, that scale factor in that direction and that scale factor in that direction. Because they're the same, and in both, we just call this a two-way stretch.
Yeah. But it gets a bit more complicated if we then change more of the numbers.
Yes. So, just FYI, if this was a 3 and the other one was still a 2, that's not a two-way stretch, but it's still just a stretch. You'd call that, if in a question if it asks you, you'd say stretch scale factor 2 in the x direction, scale factor 3 in the y direction.
Yeah, so it asks them sort of how they will in core 2 when you get there, but with matrices.
Yeah. So you just need to notice that if these are unchanged and only these are changed, it's just a stretch scale factor that in that direction.
So if we use, okay, I was going to keep some of that.
Sorry.
That's alright. So we use a different shape or the same shape?
Yeah, we use a triangle for fewer points because this one's going to be a bit harder.
So if we have a clue, lost my pen.
So it's still going to be at 0, 0. So this is at 0, 2.
Okay.
So it's got a straight line so far.
Sure.
And this is at 1, 0.
And you put these points together, now we have our triangle and origin.
Absolutely.
So now we're going to stretch it by more than what we did before.
Yeah.
So if we have 2, 3 and 3, 2.
Yep. So this is going to look quite a bit different to the other one.
It is. I still always, my first step I think is always to construct your equations for your coordinates.
Yep. So the characteristic x for each thing, each coordinate is going to change. It's going to be 2x plus 3y, and each y is going to be 3x plus 2y. Now we have to do that for all 3 of the points. I'll label them A, B, C again.
A will still be the origin, so all those changing will just stay as 0, 0.
Yep.
So there B.
And then we'll have C afterwards. So
Yeah.
B is at the point 0, 2. So we're substituting the value of x being 0 and the value of y being 2 into this up here to find an x and a y coordinate.
So I put our x value of 0 into there, and our y value of 2 into there, so it becomes 6. That becomes our x value.
For our y value, we still do the same thing here,
Mhm.
but that will still be 0. That one will now be 4 instead of 6.
Yeah.
So that will be our coordinate of B, so I'll just quickly draw that up. A stayed the same, B is at 6, 4.
Yeah.
Just wait here.
And then finally we have our C. Our C dash, because it's changed, and that is 1, 0. So our x coordinate becomes 2. So that's 3 by 0, so it stays the same.
Absolutely. So that's 2, and our y value is going to just be 3. So if I draw that in, that's it. 2, 3, it's about here. Now you see that isn't, it is not logically what you might have thought it would look like at all.
No.
It looks a bit weird, it's a bit condensed and really stretched. It looks really strange.
It looks really odd, and that's called shearing.
Yes, it's when you change multiple things within the matrice.
Which can completely change the shape as it did there.
Yeah. So there's no easy way of looking what they're going to look like. You can't look at the matrice and go, oh, it's going to look a bit like this, because it can be really strange.
It can be really, really odd. But that's not where matrices finish.
Unfortunately not. It goes on a little bit further.
A little bit further in 2D, that's where we have our reflections and rotations.
Exactly. So if we go back to our point just very quickly, just a point on a graph. But now the graph looks a bit more like this.
Yeah.
If we have a point here,
okay,
and we translate it by the vector -1, 0, 0, -1, then that means, because these are minus instead of 1, remember when 1, 1 means nothing's changed, because both the x and the y has been times by 1. Now it's minus, so the actual point will be at the same, if this is a 1, 1, say.
It'll be the same as that, but it'll be in the negative axis instead, so it'll be -1, -1. So that's like having a reflection through y minus x or something.
Yeah, it's reflected in the x-axis and the y direction.
Yeah.
So that's what that looks like.
And you could also, say, have, instead of that one, we could have 0 and 1, and 1 and 0.
That means, in this case it would just look the same. That means it's reflected in the line y equals x. But for a dot, because the y equals x line looks like that, the dot would look the same.
Dot would look the same.
But if it was, say
a
a triangle like this,
triangle or a line of sorts,
then the reflected version would be in the line y equals x.
Yeah.
So it's like holding a mirror up to the shape. I haven't drawn that brilliantly, but you know what I mean.
Yeah. But they don't just like doing those, they're a bit more complicated.
And in fact, they really don't like doing them at all. They like to give you angles of rotation.
So that's a bit more complicated. Instead, we use sort of a rule which we apply to nearly every situation, which is one I put up here.
Right up a little bit bigger. So it's a matrice like any other. This is cos theta minus sine theta. That's not cos theta minus sine theta, these are two separate things on the matrice. So that would be your x, that would be your y for your x dash. Sine theta, cos theta. And the sort of question they would ask is they might give you, bear with, they might give you a square, no, probably more like a triangle. They'll give you the point here, here, and this will probably be 0, 0, but if not, they'll give you that point anyway. And they'll say it's rotated through, say, 30 degrees. They like to be awkward. They might do any degree. 20 would be fine. They don't always pick simple ones, but 30. You do what you'd normally do to find your x and y for each of these points.
Yeah, you just substitute your values in. So in your equation for x dash would be cos 30 of your x, or 30 cos x cos 30, and then your minus your sine bit.
Put in front, x cos 30.
Yeah, and then minus y sine
30.
Yeah.
I mean, really it's sine theta. In this particular example, it's 30.
Yeah.
And your y dash, similarly, would be
x
sine theta plus y cos theta.
Yeah.
It just looks horrific, and they like to ask questions where it's rotated through a degree. So this thing I would remember. In your further maths book, it probably shows you how to derive it. If you can do that quick enough, fine.
Yeah.
I'd just remember it.
But this is one of the ones, I'd also just remember that and apply it. So I think that finishes us in 2D.
Yeah, just a brief mention, we've got to go through it, of three-dimensional now.
Yeah, we're not going to do too much drawing because it is huge, long, complicated and confusing to draw on a whiteboard.
It is. But the sort of questions they might ask you, we'll sort of roughly talk you through now. So 3 dimensions is when you have a third dimension coming out of the board. So
our third dimension, we have another axes line, which we're going to call Z.
Yep, so if you start on line X, this is Z.
And all that will change on our matrice, means we'll have sort of 3 columns. So before we had X and Y, and then our X and Y parts of X and Y. We're now going to have a Z part of both as well.
And to have no translation now, you keep the X the same, the other two don't.
Yeah, you sort of have ones for each of our main factors.
So that now means there's no translation. And yeah, as Triv said, it's just thinking about what's going on. These are still X dash, Y dash, and now you just have a Z dash.
Yeah. And you still construct your equations in the same way. We would have the X dash would just equal, well here, 1x plus 0y, 0z.
But what we've just been doing, but 3 times now.
Yeah.
And with the third being a Z. And that's the only difference.
Your drawing will be a bit more confusing, but apart from that, it is the same. You're not going to do an example because it would take ages.
It would. Most commonly what they'll do is they'll give you something like, they'll draw the picture for you, perhaps a stack of cards, and say, imagine this is on an axis, and this is say 2, 3, 4, what's the transformation? You'd say it's a stretch, because you notice it just changes the x, y and z respectively.
Then you'd say it's a stretch, let's go back to 2 in the x, 3 in the y and 4 in the z.
Exactly. You've got to think about it a little bit. I'd advise, say this was, just very quickly, this is 1, minus 1, 1. To think about what's going on to the entire shape, I'd think of a point in three-dimensional space, about here, where it's at the point 1, 1, 1. So it's 1 across, 1 up and 1 out towards you.
Yeah.
Then apply the formula to just that point to see what's going on. So you can see if it's reflected in the x direction, or the y, or the z.
It'll make it much clearer to sort of use that sort of idea.
So I would, that's my advice to you, is to always think of one point. If you want to ignore that, fine, you can just think of whatever point and do whatever. But
Yeah.
that would be my advice, just apply the formula to see what's going on.
And that's transformations.
In a nutshell. So we're going to carry on with matrices, the chapter isn't finished, so we'll see you there.
Absolutely.
That's good.